Hello, everybody, and welcome to Unit 3, which is Nuclear Chemistry. The two reference tables that we will be using for the Nuclear Chemistry chapter are Table N and Table O in your reference table packet. So, today we'll be talking about nuclear stability and nuclear decay. We'll be looking at how to determine the nuclear stability of various isotopes, and you guys will be able to identify the different decay modes that isotopes can have. So let's begin with nuclear stability. What you guys see here on the slide are two different isotopes of oxygen. We have oxygen 16 and we have oxygen 18. Oxygen 16 is a stable isotope. Oxygen 18 is an unstable isotope. So basically, this is a very common phenomenon that the different isotopes of an element can either be stable or they can be unstable. Now, those unstable isotopes are called radioisotopes because they can break down spontaneously. They can give off rays and particles and then convert into another type of element or isotope. Okay, so that's and why are they doing that? Because they want to become stable. So how do we determine if an isotope is stable or if it's unstable? Well, we use the neutron to proton ratio, which means you determine how many neutrons you have in an isotope, divide that by the number of protons. If your answer is between 1 and 1.5, then that isotope is normally considered stable. But if your answer is outside of that range, then the isotope is normally considered unstable. Another thing to keep in mind is that if you are looking at an isotope of an atom that has an atomic number above 83, then that isotope is going to be unstable. So let's practice that. If I ask you to determine whether this isotope radium-226 is stable or unstable, what you'd want to do is the first thing is that you'd want to go ahead and find out the number of neutrons and the number of protons in this isotope. So how do you do that? Well, you go to page 9 in your reference table packet, and which is where you have the periodic table, and you find out this element radium. This is what radium looks like. You look at the atomic number of radium, and that should give you the number of protons. So remember that from the atomic concepts chapter, your atomic number is the number of protons. So, and then if you want to find out the number of neutrons, once again, that's a quick review from the atomic concepts chapter. Number of neutrons equals the mass number minus the atomic number. So our number of neutrons are going to be 138 because we do the mass number, which is 226, minus the atomic number, which is 88. And that will give us 138 neutrons. That's how many neutrons this isotope has. And then your number of protons, as we mentioned, are going to be 88 because that's the atomic number. Now notice that for the mass number, I have circled the 226 right next to the radium, rather than circling the 226 that you see in the periodic table. Even though it's the same number in this case, but depending on what isotope you get, sometimes that mass number might not be the same. So please pay attention to this. If you are given an isotope, you go by the mass number that is given because that's the mass number specific for that isotope. And that's what we want to use. Okay? So now when we do the neutron to proton ratio, 138 divided by 88, we get a ratio of 1.56. which is outside of our range of 1 and 1.5, which means this isotope is going to be unstable. So this is how you figure out if an isotope is stable or unstable using the neutron to proton ratio. Now, another hint that we have for this example that should point towards the instability of this isotope is that notice the atomic number or the number of protons. That number is greater than 83. So that should point towards an unstable isotope. Okay. Now, what happens to those unstable isotopes? Well, as we mentioned, they are called the radioisotopes because they can go ahead and break down or they can decay and emit some sort of radiations or particles. And if you look at page 7 in your reference table packet, you guys have this table O. And table O gives you 6 different decay modes that radioisotopes can have, which means that the radioisotopes can either emit an alpha particle, they can emit a beta particle, a gamma radiation, neutron, proton, and positron. Now, some of the things to notice on this table. Notice their symbols. These are the symbols that we use to represent these decay modes. And then notice the notations that you have. Now for these notations, you have a symbol. For example, look at alpha particle. You see the symbol for alpha, and then you also see another symbol, which is He, and that's how we represent the helium atom. So why are we using that for alpha? Because helium atom has the same mass and a mass number and atomic number as the alpha particle has. Now, notice the terminology here. Whenever we are talking about the decay particles, for example, if we once again look at alpha, this number on the top, the 4, is going to be the mass, just like the mass number. But the number at the bottom is going to be the charge. And that's because in nuclear chemistry, we are really focused on the nucleus, and protons are found in the nucleus, and protons determine the nuclear charge. That's why our number of protons, another name that we use for the number of protons in nuclear chemistry is the charge. Okay? So if you look at all of those particles one by one, first of all, you have the alpha decay. Alpha decay has a mass of 4 and it has a charge of 2, just like a helium atom, which is why alpha particle can either be represented by that small a, or it can be represented by He, which is a symbol for helium. And notice that an alpha decay has the lowest penetration power, which means if you try to let an alpha radiation pass through something, it can be super easy to stop. You can just put let's say an aluminum in the way, and that should be able to stop the alpha radiation from passing through. So it has the lowest penetration power. It cannot get through a lot of things. And then we have the beta decay, which has a mass of 0 and it has a charge of -1, just like an electron. So remember from the atomic concepts chapter, electrons have no mass and they have a charge of -1, which is why beta particle can either be represented by that small b, or it can be represented with an E for an electron. And beta particles have medium penetration power, which means they can get through some things, but they cannot pass through other things. And finally, we have and then we have the gamma radiations, which have a mass of 0 and they have a charge of 0. So gamma radiation is just energy. Okay, it has no mass and it has no charge. It can pass through anything out there, which is why it has the highest penetration power. Then we have the neutron, just like the neutrons in an atom. They have a mass of 1, but they don't have any charge because they are neutrons. They are neutral, no charge. And neutrons are just represented by a lowercase n. And please pay attention to the lowercase, guys. If you try to represent a neutron with an uppercase N, then that would be a nitrogen, not a neutron. Okay. Next up, we have a proton. Proton has a mass of 1 and a charge of +1, just like we have the proton in an atom. Now, the mass of 1 and a charge of 1, in other words, a mass number of 1 and an atomic number of 1, is exactly the same as a hydrogen atom, which is why a proton can either be represented by a lowercase p, or it can be represented by an uppercase H for hydrogen. And finally, we have the positron. So positron is the exact opposite of a beta radiation, which is why sometimes we also say that positrons are beta positive radiations, because they have a mass of 0 and a charge of +1. So they can either be represented by the beta symbol or a beta positive, or they can also be represented by an electron. The only difference is that the positrons have a +1 charge compared to the electrons, which have a -1 charge. So we want to make sure that we also put the charge in there, okay? And the last thing for this part of the unit is if you let the alpha, beta, and gamma radiations pass through an electric or magnetic field, then your alpha particles are going to bend towards the negative end. Your beta particles are going to bend towards the positive end. But the gamma particles are just going to go straight. They're not going to bend towards anything. And why is that? Because remember our the rule of chemistry that we discussed in the previous chapter, that in chemistry, opposite charges attract each other and same charges repel each other. So an alpha particle, which is positive, would not want to go towards the positive end. It would try to go away from the positive end, and it would really love the negative side, which is why the alpha particles will bend towards the negative side. And exactly the same with beta particles, because they are negatively charged, they would try to ignore the negative side and they would love to go towards the positive side. Okay, because they're attracted towards the opposite end. Okay, so that was it for this part of the chapter, and we'll see you next time.